Yeah, okay. So today, last time, I sort of, through this SP4 example, tried to indicate the motivation behind this idea of valuation on a root datum. We only discussed it in the split case. And so today I want to begin by kind of formulating this in a broader setting. And then that's going to kind of lead us to the correct definition of what will be called the apartment attached to a maximal split torus. And then we're going to build certain interesting bounded subgroups attached to points of the apartment and analyze their structure. And eventually this will all be kind of merged together to make the building with the whole group action and study its properties. So today we'll be in the general setup. So any connected reductive group over our field. You may think about K being a local field, but do keep in mind that we will have to pass the maximal ramified or its completion later. So really, we don't want to require perfect finite residue field, maybe perfect residue field. Maximal split torus, we'll call it S. So this will, of course, be a maximal torus precisely when the group is split. But the whole point of this theory is that it handles things far beyond the split case. And we'll write S prime roughly for the part of S that lives in the derived group up to disconnectedness and maybe non-reducedness. So this will be the biggest split torus of the derived group, a maximal split torus of the derived group, the unique one that lives inside of S. And lastly, we have the so-called relative root system. We look at the S inside G, acts through conjugation, acts on the Lie algebra of G, and we look at the non-trivial weights that show up. The collection of those is always a root system. Verifying the integrality axiom for that has some subtleties when it's non-reduced, but in any event, this is a root system, and its span is exactly the space, the either rational or real vector space made from the characters of S prime. And so there are no roots precisely when this is 0, when S prime is trivial, which is to say the derived group is anisotropic. Of course, we're not going to be so interested in that case. Sorry, this is an RED for reduced. Just, if we're in characteristic P, maybe this scheme theoretic intersection is non-reduced. And so that's always, because this is multiplicative type, anyway, just take it to be this, but yes, I'm just being pedantic. Okay, so yeah, that's our setup. And so for each root A, we have this so-called root group, UA, inside of G. So what is this? Well, in the split setting, it's just a one-dimensional copy of the additive group. In general, this thing can be quite high-dimensional. So this is the unique S-stable, meaning S-normalized, smooth-connected unipotent subgroup, such that its Lie algebra is either the weight space of A or A together with 2A when A is multipliable. Okay, so as in the special case of SU3 is the prototypical example, that when the root system may have a multipliable root, then this so-called root group is not commutative. This is a huge issue, okay? When we discussed the case of split groups last time, we first thought about the vector space structure on that one-dimensional root group, and then we sort of thought about the torus action through conjugation as a kind of proxy for the scaling. In general, these things may be non-commutative, and in those cases, there's no vector space structure, but there will still be a torus action, okay? Anyway, just kind of bear that in mind. It's a sort of a technical point, but kind of important for the general theory. Okay, so we have these root groups, and the warning is, as I say, these may be non-commutative. And so I would like to now just recall this concept of valuation on a root datum. And the point is partly just to recall this notion, because you may have forgotten it since yesterday, but also just to sort of see that the way we formulated my admittedly partial list of the axioms is meaningful even when the root group is not commutative. Okay, so so we have this notion of valuation on a root datum. So this is a collection called phi. It's a collection of maps, phi sub a, from ua of k to the reals, together with infinity, for all roots a. And these maps satisfy a variety of axioms. The full list is a little bit verbose to get into. It's, of course, given in their book and other places. Let me just mention a few of the key ones. First axiom is that the only thing that goes to infinity is the trivial element. A little bit more interesting is the kind of thing that corresponds to the non-Archimedean triangle inequality was the condition that for all real numbers and all roots, if you look at the piece of the root group that gets carried to valuation at least R, that these are subgroups of UA of K. So this is a filtration by subgroups. Admittedly, in practice, these will jump at certain sets of real numbers that we don't know in advance, okay? In any event, this is some collection of subgroups. As R increase, you should sort of think about this, the bigger R is, the closer to 0 you are, the closer to the identity you should get. Okay, that's sort of the idea. Anyway, so slightly more interesting than that is, so we have a commutator relation. So if two roots are not multiples of each other, then if you look at the commutator, so I'm going to call this, sorry, let me call this U, A, phi, R. So again, this is a kind of decreasing collection. As R grows, this is a decreasing collection of subgroups of the root group. If you take the commutator of two of these for two different roots, for two different depth parameters, you know, R and S, into there, this is inside the group generated by all roots that are combinations of A and B with positive integer coefficients for the corresponding modified depth parameters. So this is over roots of the form PA plus QB for P and Q positive integers. Okay, so again, this was motivated last time from the split case by thinking about the classical Chevrolet commutator formula, which involved powers of the root group parameters. Here, there's no such thing, but this kind of containment relation is still meaningful, and so this is imposed as an axiom. Okay, so this is a condition. Lastly, so this is for all real numbers. And then the last axiom, so VR3, this has to do with the torus, how it interacts with torus conjugation on the root group. So if you hit it on the inside with conjugation by S inverse, so I'm just basically writing the formula that I wrote yesterday. So for all U and all S. Okay? Now you may be wondering, why do I put the S inverse here rather than S? And the reason is because, well, there are more axioms that I'm not telling you, one of which involves how it interacts with conjugation by the normalizer of the torus. And the normalizer of the torus is not commutative. And so then if you want this to correspond to a left action, you have to put the inverse there. Of course, you don't notice that when you're just looking at the torus, since that's commutative. But anyway, and there are more axioms, which I'm not going to list. Okay, but anyway, this gives you a flavor. Okay, so anyway, there is this concept. And let me just say, the full list of axioms has the pleasant consequence that phi is completely determined. You know, just to give an example of like an axiom that I'm not telling you, I mean, I'm not going to tell you it, right? Otherwise, it would be contradiction, but I'll give you a taste. You know, there are more axioms such as relating phi minus A and phi A. Okay, so there's some axiom about how those are related to each other, whatever form it takes on. Okay, anyway, the full list of axioms has the pleasant consequence that phi is completely determined by the valuations on the roots in a root basis. of course, I'm not addressing the question of how do you build these things. We will come to that in the quasi-split case a little bit later today. All right, actually constructing a value. So last time we sort of saw that from a Chevalley, from a kind of writing down a kind of split form of a group, if it's split, we could build these things by choosing integral bases and valuations on the root groups in a suitable way. But in general, particularly beyond the quasi-split case, it's basically impossible to write these things down, and we're not going to need to write them down. Okay, but these things are going to be a crucial tool to define what the apartment is in the quasi-split case. And the way the whole theory is going to go is we're going to ultimately, everything will be done first in the quasi-split case. And then there's going to be a theorem of Steinberg that says that over the maximum ramified extension, because the residue field is perfect, the group is quasi-split up there. So we'll have all of Bruhat-tits theory up there, meaning both the building and these various integral models that we'll be discussing. And then all of that structure will, by a very clever series of arguments, will eventually be pulled down to the original situation. Now, it is possible, and is done, for example, in Gopal's book with Tasho, that once you have the theory over the original ground field, you can use it to prove, to construct these valuations of the root datum in the general case. But they're so indirect and so abstract that it's probably hopeless to write down. Okay, but maybe it just psychologically makes you feel good. But for us, these are going to be the tool to make the apartment. Okay? Okay, so let me mention, so two sources of examples. So if the group with the maximal split choice, so if this is split, meaning S is maximal, then this has the form GK-SK for a reductive O group, a script G, and a fiber-wise maximal, a split fiber-wise maximal O torus, a script S in script G. And in this case, we saw last time, so we use these various isomorphisms subject maybe to the Chevalley commutator relations to these integral root groups to build a phi. Okay, so this is what we discussed last time, that if you're in the split situation and you choose if you choose these integral isomorphisms of the integral root groups appropriately defined to GA over the valuation ring, then we can use that to actually build such a valuation. Now, of course, you may choose different such, this choice of the U sub C's down here, these little U sub C's, right? This often goes under the name of a pinning. So subject, maybe you want to clean up the commutator relations to have very clean structure constants, for example. Okay, so if you make such a choice of these things, these are called Chevalley valuations. Okay, so if you choose a pinning of your group, which is some appropriately sensible way to trivialize all the different root groups in a nice way that interacts well with commutators, then you get this class of valuations that we discussed last time. These are called Chevalley valuations. There's a slightly broader setting in which one can make these Chevalley valuations. And so for quasi-split G, so quasi-split means there exists a Borel subgroup in G over the base field. And very importantly, another characterization of being quasi-split is that if you take the centralizer of the maximal split torus, these are so-called Levy factors of minimal parabolics, that this is again a torus. So when you're in the quasi-split case, then you can again, one has root groups. They might be somewhat higher dimensional, but nonetheless, you can actually adapt the notion of pinning to this situation. And let me just say that you can adapt the construction from the split setting. But this uses very importantly, sort of God looks down and says a whole bunch of calculations with SU3 will magically work out very nicely. And so the whole thing works. So in the study of split groups, right, one kind of SL2 somehow controls much of what happens. In the study of quasi-split groups, SU3 associated to quadratic Galois extensions controls what happens. And so there are certain calculations that one has to make using SU3, and depends whether the quadratic extension is ramified or unramified, and p equals 2 is its own nightmare. And anyway, but the point is everything works out beautifully in the end. So uses some real work with SU3 attached to quadratic Galois extensions of K. So the construction, adaptive construction using work with this to again make a notion of what we'll call Chevalley valuations. Okay, so I'm not going to give the specific description because it involves some gritty work with the nature of root groups for SU3 that I don't want to get into. But the point is, the concrete thing that we discussed last time can, with some real work with SU3, actually be shown to make sense here as well. So there's some reasonable class of valuations that are quite concrete that you can also write down in the quasi-split case. I'm sorry, so when I write SU3, I'm referring to the quasi-split version of SU3. So you start with a quadratic Galois extension and you make that kind of split-looking Hermitian form. Yeah, absolutely. Yeah, so working with quasi-split version of SU3, yes. Okay, fantastic. So now let me show you something interesting that can be done with the valuations. Let me leave these axioms up here on the board. So, so here's something kind of interesting. So let's consider this real vector space associated to S prime, the co-characters of S prime. So I claim that this acts on valuations. So here's the rule. So let me tell you what's going on here. So we start with evaluation. It's a collection of phi sub a's satisfying a bunch of these axioms. Now, you might say, well, what happens if I try to add some constants to these? Are there any conditions, constraints on those constants? Well, look here. If you're going to add a constant to this that depends on A, and add a constant to this that depends on B, so R and S are going to change, then these are going to change as well. And so then these things had better change in a compatible way if you want to preserve the commutator relation. And one can then just check as a pleasant calculation, right? Roots are in the dual space of this thing. And if you add to each phi A the constant A of V for a fixed V in here, then the commutator relation will still be preserved. So that's basically, what did I call that? That's VR2. So I'll just say CVR2. Okay, so this gives you, and it satisfies the full list. You're kind of shifting the filtration indices, but how much you shift depends upon which root you're looking at. Okay, and if you wind up getting back where you began, then V had to be 0. Because you see, if this is equal to phi sub A for every A, that would say A of V is equal to 0 for every A, but the A's span the dual space to this. So that would say this vector is killed by the entire dual space, so it would have to be 0. Okay? So this is actually a free action. But I'm only taking the co-characters of S prime. As in your book. Yes. Okay. So that's good news. So this is a free action. And we'll say that two valuations, phi prime, are, okay, well, the word, I apologize to anybody who's French in the audience, so I'll say it's equipolant. Apologies. Anyway, so that's the word I believe from the paper of Bruhat-tits. So we'll say they're equipolant if they're related through this action. Okay? Now, in the case of the Chevalley valuations, for example, in the split setting, they come from these pinnings. Okay? But any two pinnings can be related to each other through the action of a rational point of the adjoint torus. Okay? And so then it winds up being the case that if you take the lattice from co-characters of S add inside here, that simply transitively permutes the Chevrolet valuations. And that happens to also work in the quasi-split case. So I'll just say that this lattice, by S add, I mean the image of S in the adjoint quotient of G. Okay? So this lattice, which is isogenous to S prime, so they give you the same real vector space, this simply transitively permutes the Chevrolet valuations, even in the quasi-split case, not just in the split case. Fantastic. So therefore, if we consider the full orbit of the Chevrolet valuations under the real vector space, that will certainly contain all the Chevrolet valuations. That's some God-given equipollence class. That's what we call the apartment. The definition, so A of S is the this X star S prime R orbit, the equipollence class of the Chevrolet valuations. And here I'm assuming that G is quasi-split. Okay? So you have this real vector space inside of which, oh God, it's not a vector space. Sorry. It's an orbit under this action of free action of a vector space. It has no distinguished point, but within there, you have this torsor under this lattice, and that's the Chevrolet valuation. So you could sort of think about this as some kind of, it's an example. This is an affine space for this real vector space, X star S prime. It has no canonical point, okay? You might think it has a kind of lattice worth of canonical points corresponding to the Chevrolet valuations. But regardless, this is just some set upon which this vector space acts freely. Okay, so the picture in your mind is you think in R3, you have a plane through the origin, and then you have some parallel plane, right? And this parallel plane is an affine space for the actual plane, but it has no distinguished point. Okay, so this is the apartment attached to S. And so let me now observe, this has a very interesting feature, which is, let's think about the normalizer of S, okay? Well, the K points of the normalizer act on the group, and in particular, preserving the torus S, okay? And so this actually acts on the collection of valuations. So let's see how the action goes. So the way that I'm going to act on a valuation is I simply take the other valuation and then I pre-compose with conjugation on the appropriate root group, right? So this will take the root group at A to the root group at n inverse A, and then this is what we'll define to be the associated new valuation on A on the root as a function on the root group at A. Again, the reason we put the n inverse here is to make this a left action, which we have to be careful about because this n is non-commutative. Okay, fantastic. So this is an action, and then one can check that when you apply it to something that's equipollent to the original phi, then what you get is this guy plus n bar of v. We hear this n of k maps onto the Weil group of the root system, which of course acts on that vector space. I'll just call this n to n bar. Right? There's a natural action of the normalizer on this vector space, and if you have something that's equipollent to phi and you hit it with the normalizer, you get something that's equipollent to the n applied to that original phi. So this is some identity that one checks from the definitions. Fantastic. So we thereby get, so the upshot of this is that n of k acts on the, and I'm sorry, and I should have mentioned that this also takes Chevrolet valuations to things that are equipollent to Chevrolet valuations, so it preserves the apartment. Okay? Now, so this is a very interesting thing because this guy, so this respecting the action of this vector space in the sense of this formula. Okay? So this is fundamentally different from this, because usually the way you think of n of k acting on this is through this finite Weyl group quotient. Okay? However, this action in here, think about what happens on S of k inside, right? Well, the definition is using the inner conjugation by S, and one of the axioms, which has now disappeared, right, was that if you applied inner conjugation by the torus to evaluation, it changes it by the ord of A of S. Okay? So the point is, it respects this, but where S of k actually acts through translations. Let me make that more specific. So our torus maps to the adjoint torus. This is split, so this is k star tensor the co-characters of the adjoint torus. And then you could apply minus ord to the k star part. And then you get something in here, and this sits inside the real vector space, which is the same as our earlier vector space. So the upshot is S of k naturally lands in here, hits some kind of lattice, and when you look at how it acts on the apartment, it's actually acting through translations by that lattice in this real vector space, which itself has this as an affine space for it. Okay? So the thing I just want to stress is, whereas the usual action of n of k on here makes S of k act trivially, because S commutes with S prime, from this point of view, S of k is acting highly non-trivially. It's acting through translations by a lattice. Okay? So this is some kind of substantial upgrading and much more sophisticated kind of action of n of k on this thing, in contrast with this action through the Weyl group here. Okay? Fantastic. So the upshot is that we have this, this action, and so now we can proceed towards making the building in the quasi-split case, and then we'll see how those ideas adapt to the general case. Okay, so now let's assume that G is quasi-split. So the centralizer of S is a torus. Okay, fantastic. Well, a torus over a local field like K, has what's called an associated Néron model. Okay, so it's some kind of God-given best possible smooth model for that torus. In the theory of abelian varieties, there's maybe a much more widely known theory of Néron models for giving, in some sense, best possible smooth integral models for abelian varieties, having a group structure and so forth. But there's also a good theory of Néron models for tori. And so we can apply it to this. So one has this thing called the Néron model, which I'm not going to get into exactly what it is. I'll just call it script S, script Z. And correspondingly, inside of there, you strip away from the special fiber, take away all the non-identity components of the special fiber. Okay? This thing turns out to have highly disconnected special fiber, but you just take away all the non-identity stuff, and then what remains is called this identity component, and this turns out to be affine. And it's smooth. So the Néron model is always a smooth group scheme model, separated, and this identity component is a particularly special thing, and I'm going to call zk0 the integral points of the identity component of the Néron model. Okay? So this is some distinguished open subgroup, open bounded subgroup inside Z of K. So some canonically associated thing. Okay, now we can start to make, yes? Sorry, so the apartment is the full equivalence class under the entire real vector space of the Chevrolet valuation. So inside the apartment, you should visualize as like a lattice worth of these Chevrolet points, but in fact, it's an affine space for the entire real vector space. Yeah, okay, great. Okay, great. So, so now we can start to, let me make one last definition, then we can start to construct some things. So I'm gonna call GK0 the following, whoops. So we have G simply connected mapping to G. And so then on rational points, this has some image, which we're going to call GK. Is that a natural or something? So inside GK, that's just the image of this thing. And so we'll define GK0 to be this stuff from the simply connected part together with ZK0. And this turns out to be an open normal subgroup of G of K. And it's independent of the choice of S. Okay, fantastic. Okay, so now we start to construct some groups. If I give you a point in the apartment, which I will now denote by X rather than phi, then I'm going to call GK0 X is going to be the subgroup generated by, you look at the kind of depth zero, the kind of zero stage filtration in the root groups associated to the evaluation over all roots, together with Z of ZK0. Okay, so this is just some potentially crazy looking group. But let me just point out that these things, points of the root groups, always come from the simply connected cover. The map from the simply connected cover to the original group always carries root groups isomorphically to root groups. So all of these guys come from G simply connected. So this is some subgroup of this thing that I called GK0. Okay? Now, so here's the miracle. This thing, you see, ordinarily you would think if you just take a bunch of subgroups and you look at the group generated, it's something totally out of control. Okay? But you know, Tits was a kind of a master of group theory. And so there are these just absolutely awe-inspiring commutator calculations that get carried out that show that the group generated by these pieces, in a certain sense, doesn't contain anything beyond the minimal amount that that you would hope it contains. So let me tell you the theorem about the structure of this group. So there are two parts. First of all, this is actually bounded, which itself is not obvious at all. And at the same time, if you look at the part of it which lives in the open cell for a choice of positive system of roots, what you get is the minimal amount possible. Namely, all that you get in the negative root groups, you only get what you put in, multiplied in any order. In this piece, you only get ZK0. And then in this piece, you only get the contribution from the non-divisible positive roots of what you put in. Okay, so this is an utter miracle, okay, that you take these pieces, and this has to do with very clever use of the axioms for valuations and so on, okay, but it shows that actually what you get is not only bounded, but the part in the standard open cell is in fact exactly as a kind of set, is exactly under multiplication, a product of the minimal amount of stuff that could possibly be there and nothing more. Okay, so this is really quite astounding. And in fact, one can push this a little bit further. I just want to mention this because it pervades many other applications. So there's a notion of what's called a concave function. So if I assign a real number to every root along with a number assigned to 0, I'll call it concave if f of a plus b is less than or equal to f of a plus f of b whenever a plus b is also in here. Okay, this is just some notion. And it turns out that using concave functions, you can do a variant of this. So if I define GKXF, this is defined to be the group generated by going to depth f of A for every root together with ZK0. And this turns out to also be bounded. Of course, if you take the function to be the zero function, which is concave, this recovers that. But this is also bounded. And it has an analog of how it meets the open cell, which I won't try to describe here. Okay? So this is a kind of generalization. And this is extremely important because both Bruhat-tits group schemes attached to bounded subsets of apartments, as well as groups that show up in the study of Moy-Prasad filtrations, are all instances of this construction. Okay? But I must stress this boundedness is not obvious at all. Okay? But somehow, anyway, it's all quite magical. Okay, fantastic. So, great. Well, now we can put a little more structure on this apartment. You see, this has this action by x star of S. Now, in here, we have this, I don't know, we have all these affine root hyperplanes. And if you try to translate by stuff from the adjoint torus, then it'll move, because these are like roots plus integers. And if you try to translate in here by these guys, then it will actually carry the collection of hyperplanes into itself. Okay? But you could, this you could identify with this using a Chevalley valuation as a base point and transport the hyperplane structure into here. If you change the Chevalley base point, then because the Chevalley valuations are all related through this. So since this preserves the collection of hyperplanes, then on this affine space, you get a well-defined canonical collection of hyperplanes. Okay? So this kind of simplicial-like structure that we see over here has a well-defined transport over to here by using any choice of Chevalley valuation as the base point. It doesn't matter which one you choose, precisely because they're all related through this, and this action preserves this collection of hyperplanes. So this thing here has what's called a polysimplicial structure. Okay, so if you think about it as a picture of a Euclidean space, it's kind of tiled by things which, in the case that the relative root system is irreducible, are simplices, but in general, the group will roughly be a product, and it'll really be tiled by things that are like products of simplices. That's why we say polysimplicial. Okay, so this affine space has this interesting polysimplicial structure. Okay, fantastic. So now I can tell you some miraculous things. So let me first draw a picture. So if you have some kind of simplex like this, then we have the notion of what's called a facet of the simplex. What we do is you have the interior, that's the open facet. And then on each of these hyperplane faces, you take the interiors of those triangles. Those are the codimension 1 facets. Then on the edges, you just take the interior open intervals. Those are the codimension 2 facets, and then you have the vertices. Okay? So more generally, if I gave you a simplex in Euclidean space, you could decompose it into these facets of different dimensions. Okay? But they're pairwise disjoint. Right? They're not the closed things. Right? So you have the open interior, the open pieces of the codimension 1 faces with the edges removed, and so on down the line into higher codimension. Okay, so here's a remarkable theorem, which is that these groups that we've made for each point of the apartment depends exactly and only on the facet in the apartment through X. So we may then call it GK0F. Okay, so for each facet in terms of this polysimplicial structure, all the points in that facet turn out to give rise to the exact same subgroup. And if you have points at different facets, you get genuinely different subgroups. Furthermore, if one facet is inside the closure of another, then the associated groups are included the other way around. Okay? At the end of the day, this will be the stabilizer under the action of GK on the whole building, the GK0 group that I introduced earlier, its stabilizer, the subgroup of it that preserves a facet, will be this group. But we don't know that at the beginning. So we've essentially built the stabilizer groups before we've made the object upon which they will be the stabilizer groups. Okay? But this is going to be very important for getting a Tits system. In any event, so we have these subgroups, and they have this closure relation between them. Fantastic. And the second condition I want to mention is, this is the first property. And then the second one is, what happens with the action of the normalizer? You see, as we saw in the case of SP4, these simplices may have quite asymmetric structure, right? We had this 45-degree triangle, and of course, there's no way that you're going to have some group acting respecting the geometry that's going to take a right angle to a 45-degree angle. So not all vertices are created equal. So facets of a given codimension may not all be carried to each other. However, the open facets are. So the NK action on the apartment turns out to yield among its output the entire action of the affine Weyl group. So from the collection of hyperplanes, we have all the reflections in those hyperplanes. That's what we call the affine Weyl group. And it turns out that everything in the affine Weyl group comes from the action of this normalizer. Okay? On the other hand, it's known from the theory of root systems or affine root systems that the affine Weyl group from a hyperplane arrangement always acts transitively on the collection of all the chambers. So this interior one here, that's what we call a chamber. Okay, these open facets. Fantastic. So the upshot is that under this action, we get at least the full action of the Weyl group, and therefore we see that n of k, conjugates all these groups for all the chambers C in A of S. On the other hand, G of k actually transitively permutes all the different S's. And if you have an element of G carrying one S to the other, then of course the polysimplicial apartment will be carried to the other polysimplicial apartment, and so those chambers will also be carried around. And so the upshot of this is that the collection of these subgroups over all choices of S and all chambers in the corresponding apartment, this is a single GK conjugacy class inside GK0, and these are called Iwahori subgroups. Okay, so we have this nice conjugacy class. Fantastic. So now comes a fundamental theorem, which is that these Iwahori subgroups can actually satisfy a highly non-obvious group theoretic property. So if you take GK0 together with a choice of one of these Iwahori subgroups and see where it meets the normalizer, this is an example. This is a Tits system, which is some purely group theoretic notion that I won't try to define here. And its Weyl group, which is defined to be n mod n intersect I, is exactly the affine Weyl group of the hyperplane arrangement. Okay? So whatever this is a highly non-trivial group theoretic structure on this situation. And Tits systems have such fantastic group theoretic properties that you can make a polysimplicial structure that keeps track of a lot of the group theoretic information. And it turns out that the polysimplicial object attached to this purely through group theory happens to exactly match the collection coming from these apartments, as I'll describe in a moment. Corollary of this Tits system is the following, that you have something called the Bruhat decomposition. Okay, all the double cosets for a given Iwahori, in fact, always represented by the normalizer. This is a general property coming from the theory of Tits systems. Fantastic. So now I can finally tell you what the building is. So we can define it in two different ways. First of all, we have the definition building attached to Tits system. This is some somewhat abstract group theoretic device. I won't try to describe it, but actually we can just do the following. We take one choice of S, we formally think about trying to make the group act on this, and we simply impose an equivalence relation where Gx will be equivalent to Hy if the following H inverse G is in the normalizer times stabilizer at X, where if you write it in this form as n gamma, that Y is equal to Nx. Okay, so there's a slightly involved definition. One checks this as an equivalence relation. And the crucial point is that under this definition, if you put A of S in here by putting a 1 in the first spot, this is injective. And for every point in here, its stabilizer under G of K0 will in fact be this group due to how everything is set up. And this thing is covered. So under this, G acting on A of S is naturally identified with the corresponding torus. So this set is some kind of very subtle merging together of all of the apartments in some quite complicated way that has this action by G of K on it. Okay? So in any event, the point I want to make is that we create this set, and because this group theoretic data actually is a Tits system, it turns out that, so this B of G is an example of a polysimplicial complex. So it's some space that's kind of covered by these affine spaces with all this polysimplicial structure that are compatible in a nice way. And because of the Bruhat decomposition, you can deduce that any 2 points will live in an apartment. An apartment of this is defined to be an A of S for some S, maybe not the one we started with, but one of its orbits under the group, which are in fact the other apartments that we already had. Okay? So the upshot of this is that the Bruhat decomposition turns out to imply that any 2 points live in some apartment, some common apartment. Yeah. So I'm about to do the general. I realize I have almost no time left, so I'll say something about the general. But everything here is still in the quasi-split case, because that's the only context where we're able to build the apartment at the moment. Okay? In any event, so the point is any 2 points live in the same apartment. But so if I give you 2 points, X and Y, you find an apartment containing them. And so now what you do is you can pick a violent variant inner product on one apartment and then propagate it to the others. And then one can show by this mechanism, you get a well-defined function on pairs from the building into the non-negative reals, namely take the distance in some choice of apartment that contains both points. And you can show that's independent of the choice. The problem is, it's not at all obvious that this thing satisfies the triangle inequality. Because if you give you 3 points, you don't see that there's an apartment, and there may not be an apartment that contains all 3 of them. Okay? Nonetheless, because this thing is a Tits system, one can show that this gadget actually satisfies a collection of highly non-trivial properties called the axioms for an abstract building. And by using the abstract theory of buildings, you can deduce the triangle inequality for this thing, even though any given triple may not lie in a single apartment. So B of G is a building in some abstract sense. This follows from the Tits system property of the group data over there. And this can be used to show that D is not only a metric, but is also negatively curved in some appropriate sense. Okay? So the crucial thing is this turns out to be a complete metric space, and it has a metric with this non-trivial negative curvature property. And then there's a general theorem that says that if you have a sort of a group acting in a bounded way, appropriately defined, on a complete metric space with negative curvature, then there must be a fixed point. Okay, so what is the upshot of this? If I give you a bounded subgroup, it must be sitting inside the stabilizer group for G of K acting on the building. But if you actually probe a bit further, you can actually show that it must be contained up to finite index inside one of these GK0x's. But these GK0x's, you can actually build integral models for them by using a variant of the argument that I did in my first lecture. And so in fact, one can show that the stabilizer groups of all the points in the building, in fact, have a kind of integral, smooth integral model of a very canonical type. And then if you apply this over the maximum ramified extension, you can use étale descent for those integral structures to pull them down. And you can realize, so I'll just end by saying this, in the general case, you define the building to be the Galois invariance of the building over the maximum ramified extension. And inside of here, you take the facets that, this is non-empty because of the Bruhat-tits fixed point theorem, thanks to this negative curvature property. This is non-empty. Every point of this lives in some facet. If you take the invariance of the facets, these give you a polysimplicial structure on this. Similarly, you can do something with the apartments as well. You can take maximal split tori here, find very sensible choice of torus here, maximal split that contains it, take these apartments, take their fixed points, and you can wind up getting an apartment structure here as well. So you can use the entire rich structure theory here to deduce that this gadget satisfies all the axiomatic requirements for a building. And then you can infer from this structure that the analog of what I wrote there on the left is actually a Tits system down below. So it's completely backwards. In the quasi-split case, we use the group theoretic input to deduce the building structure. In the general case, we use the building structure to put a lot of geometry onto this and then can infer after the fact that all this group theoretic data, including the integral models, does exist and work well because we do it by descent from up above. So in that way, you get this entire theory, but you don't use valuations on the root datum in this setting. In the general case, you only have it up above, and then you make everything. But as Gopal would say, if you look in the book, you can derive the existence of valuations of the root datum from this structure, although it's not quite clear what you would do with it. Okay? Anyway, so that's the apartments and the associated group theoretic information. And I just want to emphasize that the existence of the integral structures on these bounded subgroups is an absolutely essential part of doing the descent to carry this out. The original paper of Bruhat-tits actually did magically manage to build these valuations of the root datum in the general case, but it was some overwhelmingly complicated thing. And things are far, far cleaner to do the descent with the building first, do the descent with the integral models, and then you can make the valuations of the root datum at the end if you care. But for all the interesting applications of Bruhat-tits theory that I've seen, it's completely irrelevant. All you need is the structure, and you don't need the valuation theoretic interpretation of the points of the apartment. Okay, I'll stop there.
So thank you very much for a great talk and for the fantastic mini course. Are there any questions?
Yeah. Okay, so there are two things to say. Sorry, okay, so there's this book. I'm not sure you would call this an exposition. So I guess I'm being arm twisted into writing up some notes for the proceedings, but I guess that's, okay. Yeah.
Thanks. Your book.
Anyway, so when I do the write-up, I'll put in some of the applications too. But anyway.
Just trying to give you an opportunity to do some.
Huh?
So I was just trying to give you an opportunity to advertise.
Okay, yes, yes, fair enough. Yes. To advertise. Gopal's grandkids want to get more profit from the book.
Any other further questions?
Okay. Yeah, yeah.
Right. If there are no,
Ah.
there is one question.
Sorry, I'm just wondering, you talked about buildings in the end,
Yes.
some abstract. So this p-adic or the Bruhat-tits buildings, do you have a axiomatic or some kind of characterization?
Let me say two things. First of all, one can give a sort of axiomatic characterization that roughly allows you to go back and forth between this kind of group theoretic information and this kind of polysimplicial gadget. So you can sort of give a list of axioms which will uniquely characterize the building. On the other hand, for various sort of classical groups, there are these, of course, very explicit constructions in terms of lattice chains. And then one can, and this is explained, for example, again in this book, which you can purchase on Amazon. No finder fee for me. They have a whole chapter which discusses these concrete interpretations, which is useful for some purposes. But I'll just say that for many, like for a lot of it, they give very nice applications in chapter 10, like Galois homology or existence of anisotropic maximal tori and various things. And none of those use this, these concrete interpretations. They just use the fact that it's sort of like when you work with grid systems, right? You just want to eventually think about Euclidean geometry and drawing line segments, and this is usually what you need, right? So you don't need this, like I remember I once saw in some book, somebody tried to like actually draw a picture of some like two-dimensional building, and so it was some kind of horrible mess. But I find it hard to believe that could ever be useful to do anything. Maybe I'll just say one last thing on that direction of the visualization. When the residue field is finite, right, then every point has a neighborhood through which there only pass finitely many of these hyperplanes. But once the residue field is not finite, like all bets are, it's just a vastly infinite array of these things. And so I think it's probably very hard to try to literally visualize it. But for applications, you just kind of work in one apartment at a time, and that's often quite sufficient.
All right. Let's thank the speaker again.